Listen up. If you're serious about boosting your CUET rank, there's one chapter you absolutely cannot afford to get wrong. Coordination compounds. This chapter is an absolute goldmine for marks, but here's the catch. It's also where so many students get tripped up. Let's fix that. Right now.
Take a good look at this. It looks pretty simple, doesn't it? But I'm telling you, a tiny misunderstanding right here, that's the difference between a top percentile score and just being average. So what really decides the shape of this compound? Is it the 6 ammonia molecules inside? Or do those 3 chlorine ions on the outside have a say too? Think about it, because your answer reveals a lot about how prepared you really are.
You know, the secret isn't even about the atoms. It's all about these, the square brackets. Stick with me for just a few minutes, and I promise you, by the end of this, you'll understand the secret power of these brackets and you will never fall for this common trap again.
So, that question I just showed you, that wasn't just some random problem. Think of it as a quick test, a diagnostic, really. It exposes a fundamental weakness that CUET examiners love to target. We're about to fix that, right now, starting from the ground up.
All right, first things first, let's lock in a core rule. I want you to think of everything inside those square brackets as a team, a single, inseparable unit. It's called the coordination entity. In our example, the cobalt and its 6 ammonia buddies, they move as one. They react as one. They are one single chemical unit. This is non-negotiable.
Okay, to crush any question from this chapter, you need a solid toolkit. And really, it just comes down to understanding 2 main players. Once you get their roles down, you'll be able to solve pretty much anything they throw at you. Let's break them down.
So first up, meet the king of the complex, the central metal atom. It's usually a transition metal, and it's always written first inside the brackets. What's its job? Simple. It accepts electron pairs. It's a Lewis acid. This guy is the boss. It's the one calling all the shots, dictating the geometry, the magnetic properties, basically all the important stuff.
And hey, if the metal's the king, then the ligands, well, they're its loyal supporters. They're the molecules or ions that bond to the metal. Their entire job is to show up and donate electron pairs, which makes them Lewis bases. And they can be neutral, like ammonia, or they can have a charge, like a chloride ion.
And this, right here, this is the core dynamic. It's like a perfect yin and yang. The metal is the Lewis acid. It accepts electrons. The ligand is the Lewis base. It donates them. The metal dictates the shape. The ligands attach to it. Master this simple relationship, and you've mastered the foundation of this whole chapter.
All right, time for a pause and think moment. This is a classic CUET trap, so listen closely. You see a ligand with a charge like Cl negative. Does that mean the metal's oxidation state is automatically decided by that charge? The answer is a huge, absolute no. Don't ever confuse the charge on a ligand with the final oxidation state of the metal. They're connected, for sure, but they are not the same thing.
Okay, let's reset for a second. I'm about to give you a pro tip, a mental model that the top rankers use to just see these compounds clearly. From this moment on, I don't want you to see square brackets as just symbols. I want you to see them as the walls of an arena.
Think of it like this. Everything inside those brackets, that's the arena. That's where all the real action is happening. The central metal and the ligands are bonded together in there. And anything hanging out outside the brackets, they're just spectators. We call them counterions. Their only job is to watch from the sidelines and keep the overall charge balanced. They are not in the game.
And this is the absolute key for your exam, so lock this in. The arena, that coordination sphere, is in charge of all the important stuff. The geometry, the coordination number, the magnetic properties, all the big-ticket items. The spectators, the counterions outside, they only affect things like overall charge and maybe solubility. They have zero, and I mean zero, say in the geometry.
6. Just 6. What on earth does this number mean for our complex CONH3 3+? This single number is the entire key to its shape.
That number, my friends, is the coordination number. And listen, it's not just about counting ligands, it's about counting the number of direct bonds to that central metal. So, since we have 6 ammonia ligands and each one forms one bond, the coordination number is 6. For something like PtCl4 2-, it's 4. It's all about what's directly connected inside the arena.
Okay, another pause and think. And this one's a mini challenge. You ready? There's a ligand called ethylene diamine, or EN for short. It's bidentate, which is a fancy way of saying it bites down on the metal in 2 spots. So if you have 3 of these EN ligands attached to chromium, What's the coordination number? Is it 3 or is it 6? Come on, think about it. Each EN makes 2 bonds, so 3 of them, that makes 6 bonds. The CN is 6. See? Easy once you get it.
All right, let's talk about the one skill that's like a superpower for this chapter, calculating the oxidation number. Seriously, if you can nail this quickly and accurately, you are way ahead of the game. Let's learn the hack.
It's a super simple 4-step recipe. You follow it every single time and you can't go wrong. Step 1, the metal's oxidation state, we're going to call it X. Step 2, add up the charges of all the ligands inside the bracket. And remember, neutral guys like ammonia are just 0. Step 3, set that whole sum equal to the overall charge of the complex. And step 4, just solve for X. That's it, every time.
Okay, your turn. Let's practice. What's the oxidation state of iron in FeCN6 4-? Remember, each cyanide, or CN ligand, has a charge of -1. The whole complex has a charge of -4. Lock in your answer. What do you think? +2, +3, -4? Go on, commit to one.
And the answer is +2. If you got that, fantastic job. Let's just quickly break down why. You have X for the iron plus 6 cyanides, which are each -1. The whole thing has to equal the overall charge, which is -4. So X minus 6 equals -4. Do the simple math, and boom, X is +2.
All right, team, we've built our toolkit, we get the arena and the spectators. It's time. Let's go back and absolutely crush that original score killer question that started this whole thing.
So here it is again, the final showdown. In the compound CONH36Cl3, what truly determines its geometry? Now you have everything you need to answer this with total confidence.
And the answer, now that you know the secret, is incredibly simple. The geometry is decided only by what's happening inside the arena, inside the square brackets. Only the coordination sphere, CONH3, 6, 3+.
And there it is. We've closed the loop. The 6 ammonia ligands are inside the bracket, directly bonded to the cobalt. That gives it a coordination number of 6, and that is what dictates the geometry. And those 3 chlorine ions, they're outside. They are just spectators. They balance the charge, sure, but they have absolutely no say in the shape. Those square brackets, they were the secret all along. They're the boundary line. They literally tell you what's in the game and what's just watching from the stands.
Okay, so what do you absolutely need to remember for your CUET exam? Let's do a quick-fire recap. 1. Everything inside the brackets is one team. 2. Only that team, the coordination sphere, decides the geometry and coordination number. 3. Anything outside is just a spectator balancing charge. And 4. Master that oxidation number calculation. I guarantee you'll see it, all right? Take these core ideas, drill them with your practice questions, and you are going to be unstoppable in this chapter. You've got this.